we've often looked at surfaces this semester, often two-dimensional surfaces, but that are living in a three-dimensional space. And we've really had two ways of viewing those. I could have z being some function of x and y, and my surface could be the graph of this function. So, just as an example, if z is x squared plus y squared, I'm getting my lovely paraboloid. Okay. Now that's a two-dimensional surface. It has surface area, doesn't have any volume, doesn't take up any three-dimensional space, but it lives in three space. And you'll notice that in describing it, I need three variables because the points that are on the surface live in three space. So they have an x, a y, and a z component. Okay. So here, the number of variables that I'm using to describe this matches the space in which the surface lives rather than matching the dimension of the surface itself. It's a two-dimensional object. Now we've also seen things like a level surface of a function of three variables. So I could have g of x, y, z equals some constant. Great example here is just x squared plus y squared plus z squared equals 1. I recognize that's the unit sphere. Now again, that's a two-dimensional object. We're not talking about the solid sphere, we're talking about just the surface of that sphere. It's a two-dimensional object living in a three-dimensional space. This way of describing it uses three variables, matching the number of variables to the dimension of the space in which it lives, but not to the object itself. It's a two-dimensional object. Well, in 16.6, we're going to take a look at parametric surfaces. With parametric surfaces, even though our surface is going to live in three space, we're going to parameterize it, which means we're going to describe it in terms of two variables. So we're going to match the number of variables that we're using to the dimension of the object, rather than to the dimension of the space in which it lives. So we're going to have something like this. We'll have the UV plane. U and V are going to be my parameters. Sometimes I'll use other names if I'm using something that already sort of has a name associated with it, but U and V are sort of my go-to. And then here's three space with its X, Y, and Z system. Okay. So I'm going to be able to map some region here via a function of two variables to some potentially curved surface that I have over here. Maybe a paraboloid, maybe a sphere, something like that. But basically what I'll be doing is I'll be describing x in terms of u and v. I'll be describing y in terms of u and v. And I'll be describing z in terms of u and v. So I'm only using two variables, but to describe the three coordinates of a point in three space. Okay. So what I want to do is spend some time looking at some common parameterizations that we're going to be working with. So one thing that's fairly common would be to have a constant surface in either cylindrical or spherical coordinates. In that case, the parameters, the two variables that I'm going to use, are the non-constant variables in that system. Now, what do I mean by that? Well, let's take a look. Let's let S equal the unit sphere. Okay. So I know that in spherical coordinates, that's just a constant surface. I can describe that by saying rho, the distance from the origin, has to be 1. But I also know that I can describe x, y, and z, the rectangular coordinates for a point in 3 space, in terms of my spherical coordinates. X is rho sine phi, remember that's r, times cosine of theta. But if rho is fixed at 1, I can sub in a 1 for rho, and then I've just got sine phi cosine theta. So I've just described x in terms of these two variables, theta and phi. Same thing with y. In general, I know it's rho sine phi sine theta. But if rho is constant at 1, I don't need to write rho. I can write 1. So I'm getting sine phi sine theta. And z is rho cosine phi. But if rho is fixed at 1, that just becomes cosine of phi. So I've described x, y, and z in terms of just two variables, theta and phi. Now what's happening here is I've got my theta phi plane. Because if theta and phi are the only variables I'm working with, that's describing a two-dimensional system. Okay, so theta and phi don't take on their role as spherical coordinates until we're over in 3 space. I'm going to think of them as rectangular coordinates in the theta phi plane. And if I take the rectangle, where theta just goes from 0 to 2 pi, and phi goes from 0 to pi, that rectangle, via this transformation, R of theta phi, is going to map to the unit sphere. Pretty cool. Okay. So, and of course, if I used a larger region here, what would happen is I'd just wrap around the sphere multiple times. Okay. But that would map to the unit sphere once. Now, I kind of like to explore that mapping just a little bit because that's kind of wonky. How does this actually occur? How does a point here figure out where it ends up on that sphere? Now, you'll notice right now I've got this written as just a triple of functions. You can do that. You could have your parametrization written as x is this, y is this, z is that, or you could have it written in vector form. R of theta phi would be the vector sine phi, cosine theta, sine phi, sine theta, cosine phi. And just like with vector functions of one variable, I'm going to identify the vectors that are my outputs with the points that would be the tips if they're drawn in standard position. So I'm not going to draw a bunch of arrows, I'm going to draw a bunch of points. Okay, I'd like to understand how this mapping works. And so one thing we can do is we can look at things like the constant phi curves. Let's take a look at if phi is pi over 2. So if phi is pi over 2, I'm just looking at that horizontal line segment right here. I'd like to see what points that maps to here. So I'm going to look at, R at theta pi over 2. So I'm going to keep theta as a variable, but just let phi be fixed at pi over 2. Now sine of pi over 2, oops, here we are. Sine of pi over 2 is 1, so I'm just going to get cosine of theta for my x value. Let's see. Cosine of pi over 2 is 0, so 0 times sine theta is 0. I'm getting 0 for my y value. I'm sorry. I'm not plugging into cosine. It's still sine. I'm so sorry. Sine of pi over 2 is still 1. Times sine of theta would give me sine of theta. Here's where I'm plugging phi into cosine. Cosine of pi over 2 is 0. So my z value is fixed at 0. So this is actually just a parametric curve because we've turned it down to just one variable. So I'm describing x, y, and z in terms of one variable. This is the curve that this line segment would map to. And I can recognize that that's just the unit circle in the xy plane because z is fixed at 0. Let's see what happens if I pick a different phi value. Let's maybe pick phi equaling pi over 4. So here was pi over 2. Let's look at pi over 4. Okay. So if phi is pi over 4, I'm going to get r of theta comma pi over 4. And so let's see. That's going to be sine of pi over 4 is just root 2 over 2 times cosine of theta. Sine of pi over 4 is still root 2 over 2, but now I'm multiplying that by sine theta. And cosine of pi over 4 is root 2 over 2. Well, I recognize that too. This is going to be in the plane, z equals root 2 over 2. So we're going to stay at that fixed height, okay? But then this is just a multiple of sine and cosine. So we're just drawing a circle in that plane. So it looks like horizontal lines here, which are what I get if phi is constant, map to circles going around the sphere here. Kind of cool. Let's take a look at if phi is equal to pi. If phi is equal to pi, now we're looking at this right here. So I would get, let's see, I can keep this up but make it take up less space. So I would get r of theta pi is equal to, well, sine of pi is 0. Sine of pi is still 0. Cosine of pi is 1. So I'm getting just a single point at the very top of that sphere. That kind of makes sense. What's happening is, I'm sorry, cosine of pi is -1. I'm still getting a single point, but I'm getting the single point down here at the bottom of the sphere. If phi were 0, if I were looking at this curve, then I'd also be getting 0 and 0, but then cosine of 0 would be 1, and I'd be getting that point. Okay. So essentially, all of these horizontal line segments are mapping to circles. It's just that the one at the very bottom, when phi is 0, and the one at the very top, when phi is pi, are degenerate circles, just a single point at the very top or the very bottom of the sphere. So this is where I am when phi is 0, and then as we rotate, as phi increases, we keep getting these circles until this is where we are when phi is equal to pi. Kind of cool. Now let's take a look at what happens if theta is constant instead. So I can look at my constant theta curves. Let's just pick a nice easy one. Let's let theta equal 0. So if theta, oops, let's get a marker that writes better. If theta is equal to 0, I'm looking at r of 0 phi. So let's see, that's going to be sine phi times cosine of 0. Cosine of 0 is 1, so I'm going to be getting sine of phi. Sine of phi times sine of 0, well, that's just 0, and then cosine of phi. Well, so I'm seeing sines and cosines in the plane where y is equal to 0. Okay. So x is cosine phi, y is sine phi. That would just be drawing a circle in the plane where y is equal to 0. But phi is only going from 0 to pi here, because I tried to make it match what my spherical coordinates would be. And in general, when you parameterize a surface, you want to parameterize it once. You don't want to have 20 points over here that are covering this and wrapping around it 20 different times. You want to get all the points pretty much just once. Okay. So if phi is only between 0 and pi, sine of phi has to be non-negative. So sine of phi is going to vary between just 0 and 1, whereas cosine phi, which is my z value, varies between 1 and -1. So what's going to happen here is I'm getting just the front half of this circle right here. If I were to look at theta equals pi over 2, so I'm looking at r of pi over 2 phi, I get sine of phi times cosine of pi over 2 is 0. Sine of phi times sine of pi over 2 is 1. Cosine of phi. That's going to be drawing a half circle. Again, just half of a circle because of the restrictions on phi. That's going to be drawing a half of a circle in the plane where x is equal to 0. So that's in the yz plane. And here my y values are strictly positive. So that's this half circle. And if I chose something in between, I'd just be getting a half circle basically in the half plane that has theta equaling whatever I'm holding it constant at. So it's kind of an interesting way of getting the sphere, but that's how this parametrization gives us the sphere. And for the most part, each point on the sphere is going to have just one point over here that maps to it. The exception to that are the very top and the very bottom points. They both have an entire line's worth of points that are mapping to them.